Let's consider some examples of the strong electrolytes. That means some compounds that are strong conductors or good conductors. Now, you consider the strong acids. Strong acids. Now, when we say the electrolytes, we are considering both acids, both salts, both base, because we are talking about acid, base, and salt. So let's consider some of the strong compounds and the acid that conduct electricity. Example, we have the HCl, we have the nitric acid, HNO3, nitric acid. We have the sulfuric acid, H2SO4. These are all examples of strong acids that form strong electrolytes. Now let's consider strong base. With a strong base, we have the sodium hydroxide, we have the potassium hydroxide, we have the calcium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide. We have all this. So we have all this. Now, let's also consider the soluble salts or the strong salts. We have the what they call sodium nitrate, or if you, in other words, you can say sodium triosonitrate acid, ozonitrate salt. So NaNO3. We have NaCl. We have NaCl. We have copper sulfate salt. These are all examples of strong salts. These are all examples of strong salts. So please, all this will be uploading on our YouTube listing. So if you perchance you didn't, your network was misbehaving and you want to go back, you can just go there and go and download or go and read, go and watch. Please, when you go, don't forget to subscribe. So please make sure you subscribe. That is all. Now let's also consider some weak electrolytes. I've already explained what weak electrolytes are. Weak electrolytes are poor conductor of electricity because they ionize only partially or incompletely. And examples are citric acid, citric acid, citric acid. An example is a citric acid. Another example is 1,2. So 1,2 be ethanoic acid. Example of weak acid, ethanoic acid. Ethanoic acid. Ethanoic acid is CH, I don't know, CH free, CH free, COO, CH free, COOH, COOH, ethanoic acid. Ethanoic acid. This is a weak acid or weak electrolyte. You can also talk about hydrogen sulfide or hydrogen sulfide, which is H2S. Hydrogen sulfide, H2S. H2S is one weak acid. We can also talk about carbonic acid or H2CO3. 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 Or in other words, you can say triosocarbonate acid. Triosocarbonate acid. Triosocarbonate acid. Now let's also consider some weak base. Some weak base. Some weak base. Example of weak base, we can consider Na free, Na free, NH free, sorry. Ammonia, NH free. NH free. You can also consider amines or amines. There's a spelling. When you do organic chemistry, you learn all these things. So a large people have taught them that. So that is it. So water itself is a weak electrolyte. It can either act as a weak base or a weak acid. And we know that water is one of examples of the amphoteric substances. They can either act like an acid or act like a base, depending on the situation. And so that is it. Now, from here, we are going to talk about in the pH scale, pH scale, pH scale, pH scale, pH scale, the pH scale. Now, when we say the pH scale, we've all learned, or we all know little about pH scale. That's how I write it all. pH scale, small p, capital H, scale. Now, it is normally a scale which is used to express the acidity or the alkalinity of a solution. So the pH scale is normally a scale. And when we say a scale is a wide range of numbers or a wide range of measurements that is able to determine whether something is this or something is that, and based on how it is programmed. And so there's a scale which is used to express the acidity or the alkalinity of a substance or of a solution. And so that scale is what we call the pH scale. Now, the pH scale normally measures the hydrozonium ions concentration in a solution. It measures the hydrozonium ions concentration in a solution. It also measures what we call the H, the hydrogen ions in a solution. Now, the pH scale is a number scale, and this one is a number scale. It normally ranges from 0 to 14. It ranges from 0 to 14. So the pH scale is a number scale that ranges from 0 to 14. So it doesn't go above 14 and it doesn't go below 0. Now, it has a point where it is neutral. The number 7 is neutrality, and that is normally called pure water. So pure water has a pH of 7. It has a pH of 7, and it is neutral. That is, it's neither acid, it's neither base. It is neutral. That is it. So pure water is normally neutral. It has a pH of 7. Not in every case, maybe it might go over, but it should be in a range. When you study engineering, you know all this things. So if you have your pH, they are in graduations, or they are in graduations. So maybe here 0, 1, 2, 3, 4, this thing. So maybe here 7. Maybe here is 14. Here 0. Now, if any when we put what do you call it? When we put any solution on this, and it falls within this range, that means from 0 to 6.9, then we say that the substance is acidic. Now when we put it and it falls from this, it falls between this number. When we place in the solution and it falls within this number, 7.1 to 14, then we are saying that it is basic or it is base. Now, however, that's how it works. Normally, in order of increasing, that's how it works. With our acidity, there's the order of increasing. So there's the order of increasing. That means it increases to the 0 point, and with the base, it increases to this point, to the 14th mark. Now, this to say that if you have, when you check and maybe you have, the number was maybe here is 5, here is 6. The number is maybe 6, and that means this is a weak base. Normally from 5 to 7 or 5 to 6.9, normally they are weak base. They are weak base. Now from normally 3 to 1 or 3 to 0, that means they are strong acid. Sorry, from here to here strong base, strong acid, weak acid. Then from here to here is strong acid, and so that is it. So from this, so the smaller it is, the higher its acidity. So that when you have 0.1, then that means its acidity is high. Let me put it that way. So if you have 1, then that means it has a high acidity. If you have 2, it has a high acidity. 3 has a high acidity. The more it goes, when it goes up, then this now when you have 6 point something, that means its acidity is nearing neutrality, and that means it's what do you call it? It becomes a weak acid. It's an acid though, but it's weak. Now when you have this one, so here to 8, 9, 10, they are all weak base. Now when you start getting to the 13, 14, 15, and the rest, they are all, what do you call it? They are all strong base. They are all strong base. They are all strong base. So that's one. The order of increasing is from year to year, and year to the order of increasing is from year to year. So 8 to 7 is the order increasing, and year to 6 to 0 is the order of increasing. So order of increasing is from year to year. And so here is weak, 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 strong, 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 strong. That's it. Year 2 is weak, 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 strong, strong, strong. That's how it works. I hope you are all getting it.
Yes.
So that is it. Now, apart from the pH scale that we use, we also have one other thing that we use. We call the universal indicator. It is also used to measure the pH of substances. Universal indicator. It can be in a paper form. It can be in a solution form. Depending on what the experiment you are doing. It can be in a paper form. It can be in a solution form. Now we are saying that universal indicators are unit tests. Now when we say unit test, that means single test indicator. And it's a mixture of indicators which can indicate pH values, usually over a wide range of about 3 to 11 by successive changes of color. So that one too, it's normally is a unit test or mixture of indicators which can indicate pH values, and it is normally usually over a wide range of about 3 to 11. And we are able to, and by it happens by a successive, what do you call it, color change. So that one, before you can be able to know that it's an acid, unless there is a color change, before you can know that it is a base, unless there's a color change. So the color changes, what do you call, defines how we are going to, or defines, or should tell you that okay, this is a base or there's an acid. So the color changes, that's the magic. That's the magic under universal indicators. Now, where you have a colorless liquid, we employ the use of the indicator in a solution form. So where you have a colorless liquid, for instance, if you have water and you want to, water is colorless, or you have a solution and it's colorless, and want to check whether it is acidic or it is base, what we do is you drop about 3 or 4 drops of, what do you call it, of the indicator solutions into the colorless liquid, and as a result, when there's a color change, that will tell you that okay, your substance is acidic, or your substance is basic, or so on and so forth. That is it. So when you have that, now if, for instance, if you have the scale like the pH scale, normally when there's a color change, and it ranges from maybe, when there's a color change to maybe red, then you know that your solution is an acidic solution. But that means when it is red, and that means the range is between 1, or is between 0 to 4. Then you know that your range is normally between 0 to 4. When it is orange, then you know that your range is 5. That means we are talking about the acidity. It's 5. When it is yellow, then you know it's 6. When it is green, then you know it's 7. Now, when there's no color change, then definitely it will be neutral. Now, when you get to, when it is blue, then it's, when it's blue and it's 8. When it is blue, then it's 8. Then that means 8 means that it is a weak base. So 8 is weak base. 9 is indigo, and 10 to 14 is violet. They are all alkaline. So the alkaline starts from blue to violet, blue, indigo, violet, and what do you call it? Then the acidic also starts from red, orange, yellow, green. And I think when I just checked, you realize that you can use the Roy with red, orange, yellow, green, blue, indigo, violet. You use the Roy with. So if you are starting from here, let me, because you can't memorize all these things, so you just have to use a Roy with too. So, oh. So when we have something like this is Roy with. So R, orange, yellow, green, blue, indigo, violet. I hope you can see it. So let's say in between in between the ROIC and the GBIF is what you is the distance, is the neutrality, which is number 7. Now you know that the whole of this part is constitute of that of the acidity, and here is the alkalinity. And so here 0 to 4 is normally red, and this we can just see it as a strong acid. This one is 5, is also an acid. Now this one is also 6. 6. So I've been informed that the 7 is green. So when it is green, then that means it is neutral. Then 8 is green. 8 is blue. Sorry, 8. So here is 8. So the green is 7. Oh. So you have Roy and you have GBIF. So 3 here, 3 here, and the green in between is the 7. So let me write the G here. Let me erase it. So normally when you put it into the solution and you get green, and that means the solution is neutral. However, when you get a different distance apart from this is 9, and here is 10 to 14. 10 to 14. So just put the ROIC GBIF here and just know that the green, there's 3 here, there's 3 here. The green here is neutrality. So everything you get here. So the first one, red, is 0 to 4. So when you get anything red, then you know that it's a strong acid. When you get anything 5, you know that it's nearing a weak acid. Then this is also a weak acid. Yellow is also a weak acid. Now when you get 8, you know it's a weak base. When you get 9, or when you indicate when the color changes to indigo, you know they are talking about a weak what do you call it? A weak base. Then from here to here you can talk about the distance. So that's the universal indicator.
Gideon.
Who is that?
The slide I give you come.
So that's it. So when you're using a pH meter, an electrolyte of the pH meter is normally dipped in a given solution, and the pH is, so you dip the part which the electrode part, that means the part that connects. You dip that part. When you're using a pH meter, you dip that part in the solution, and when you dip it in the solution, the pH is registered on the scale directly. So that's how the pH is done. And so that is it. The rest is maybe experiment. Let's do our last set of this thing. Now let's also talk about, we also have another indicators. We also have what we call the acid-base indicators. Acid-base indicators. After the another universal indicator, we have acid-base indicators. Acid-base indicators. Now before that, when you're doing an experiment, these are 1 or 2 precautions you have to take when you're using the indicators. Too much or too little of the universal indicator must not be added to the solution. So don't add too little, don't also add too much. And so that is one or 2 precautions we are going to use. Now let's consider the acid-base indicators. The acid-base indicators are normally generally weak complex organic acids or base. They are normally weak complex or organic acid or base. Now we have 2 examples of acid-base indicator we are going to consider. We are going to consider the phenolphthalein indicator, which normally exists as an as a weak base, a weak acid, sorry. And we're also going to consider methyl orange, which also acts or which also represents a weak alkali or alkaline, a weak alkaline. And so the phenolphthalein, because we are talking about acid-base indicators, the phenolphthalein is normally a weak acid indicator, phenolphthalein, and the methyl orange is a weak base indicator or weak alkali indicator. So let me spell it so that you won't just listen. Phenolphthalein. There's phenolphthalein. E before I. There's an acid indicator. There's an acid indicator. Weak acid indicator. Weak acid indicator. Then we can talk about the methyl. Methyl orange. Methyl orange is a weak alkali. A weak alkali indicator. Now, so that is it. That is it. And we are going to use them in solutions. And let me just show you. Let's just move straight to how it reacts. Now, so if you have a solution and you dip or you put droplets of what do you call it, a phenolphthalein in that solution. Now, when the solution is acid, for instance, when you put a methyl orange, indicator in an acid solution, what the acid is going to do is, what the solution is going to do is there's going to be a change to red. Now, when it changes to red, methyl orange definitely will be orange. Methyl orange is orange. So when you put methyl orange in, I hope you can hear me. When you put methyl orange in any acid solution, it will change from the orange to red. There will be a color change to red. Now, when there's a change to red, then it means that the solution is an acid solution. Now, when it changes to yellow, then that means the solution is an alkaline solution. So if you put methyl orange, droplets of the methyl orange, already we know that methyl orange is as a weak alkali, what do you call it, indicator. When it is placed in the solution and there's a change to red, or the solution changes to red, then that means we right away we can know that the solution is an acid solution. Now, however, when it changes to yellow, then we are saying that the solution is a base or alkaline solution. Now, when we also put phenolphthalein in acid, because already the phenolphthalein is what we call is an acid. It's an acid. What do you call it? It's an acid indicator. It will be colorless. There's no color change. Now, when there's no color change, immediately you see that there's no color change, then you know that the solution you are talking about is an acid. Are we getting it? It's an acid. Now, when you put it in a solution and it changes from the colorless to red, then that means the solution is an alkaline. That means the solution is an alkaline. Now, let me go over again. When you have a phenolphthalein and you put it in a solution and the solution doesn't change, it remains colorless, then that means the solution is an acid. However, when the solution changes to what do you call it? Changes to red, then that means the solution is an alkaline. It's an alkaline. Unlike the methyl orange, where when you put it in a solution and it changes to red, you know that the solution is an acid. When it changes to yellow or it maintains its orange color, then we are saying that it is base. That's how it works. You know, orange and yellow is very close. So that's how it works. Now, litmus paper. I know you know how litmus paper works. When litmus paper, when you put acid solution on litmus paper, definitely it will change to red. When it changes to blue, then you know that it is an alkaline solution. However, when it is still purple, then that means the solution is neutral. Let me put it that way. That means the solution is neutral. And the universal indicator too, as I've already said, when you put it in an acid solution and it changes to red, then you know that it's an acid. When it changes to purple or blue or indigo, then you know that it's an alkaline solution. However, when you put it in it and it is still green, then that means it is neutral. When you put it in it and it's still green, that means it is neutral. And so there's a little about indicators I'm going to talk about today. I'm tired. Frankly, I'm tired. Next week we are going to talk about ionic products of water. I think that will be our last topic. That one is calculation aspect. So when we are done, if you have time, maybe we might end up doing. Maybe we'll do buffer solution. After that, we'll do buffer solution, calculation of buffer solution. Then we are done. Then we'll do solubility. We continue solubility. Then if you are able to finish, I think after solubility, maybe equilibrium. Oh yeah, or something. So that is it. So this brings us to the end of the.
Oh,
Who said oh?